We're starting with the new module called network theorems. Okay, that is module number 2. Fine. In module number 2, we have 5 different network theorems. Fine. And every network theorem has its own advantages and are applicable to some specialized networks or circuits. Okay. The first theorem under that we are looking at is Thevenin's theorem. Let's look at the definition of the Thevenin's theorem. Thevenin's theorem states that a linear two-terminal network can be replaced by an equivalent network consisting of an voltage Vt in series with the resistor Rt. Okay, any linear two-terminal network you take. It's not, yeah, any linear two-terminal network you take. That means what are linear two-terminal networks? See here, the networks that we have been seeing or the circuits that we have worked out with mesh analysis, with node analysis, super mesh, super node, or the problems that we took for source transformation, or the problem or the networks that we took for the star delta convert. They're all linear circuits. Understand? All linear circuits. So this is a linear. What is two terminal? If there are two terminals out like this. For example, see here, this is two terminals. There are two terminals, right? So if you just take this much, it is linear circuit. So if you take two terminals out like this, it is linear two terminal network. Everybody understand that point? So take a linear two terminal network. Okay. So such a linear two terminal network can be replaced by a resistor RT in series with the voltage source Vt, which is called as Thevenin's voltage. This is called as Thevenin's voltage, and this is called as Thevenin's resistance. Fine. Any linear two-terminal network can be replaced by the Thevenin's resistance in series with the Thevenin's voltage, which is the open circuit voltage across the terminals AB. AB are open circuit, right? So if you find out the voltage across these two terminals, then it is called as open circuit voltage. Everybody understand that point? So what is Thevenin's theorem telling you? Thevenin's theorem very clearly tells you that any linear two-terminal network can be replaced by just a resistor in series with a voltage source, where this voltage source is the voltage that we find across the open circuit terminals. And RT, how do you find out RT? RT has to be found out as this. Here, RT is the equivalent resistance at the terminals when the independent sources are turned off. I'll be talking about that when we solve problems. So turning off the independent sources means if there is a current source, you have to open circuit that. If there is a voltage source, you have to short circuit that. Okay, so if you open circuit and short circuit these sources, you'll be left with only the resistors. So you have to find the equivalent resistance, and that equivalent resistance is your RT. Everybody understand that point? And what is Vt? Vt is the open circuit voltage. Everybody understand this point? I hope it's clear to you. Fine. So if the independent sources are there, this is how we calculate RT. Suppose the circuit consists the dependent sources, then we find out RT by finding out VOC by ISC. Let's not look into this as of now. Okay, let's look at the dependent sources circuit later on. First, let's understand what is Thevenin's theorem, how to calculate Vt and RT. Once we calculate Vt and RT, okay, so it is as good as finding out your Thevenin's network. Okay, so this is a Thevenin's network. Any linear two-terminal can be replaced by a Thevenin's network. So how to find out the Thevenin's network is what we will be doing now. Everybody's okay with that? Yeah, this is the problem. Just copy down this problem. Okay. See, this is where we need to find out the Thevenin's equivalent network. For finding out the Thevenin's equivalent network, what do we need? First, we need, see here, everybody just look at this. We need a linear two terminal network. What is linear two terminal? See, if there are two terminals out like this, It is linear two terminal network. Okay, so let us give this AB also. So this is AB. So what is Thevenin's theorem telling you? Thevenin's theorem tells you that, okay, any linear two terminal network can be replaced by a voltage source in series with a resistor. That resistor is called RT, okay, and this voltage source is called VT, which actually is your VOC. What is VOC? Is this? See here, these are open circuit terminals, right? So this is linear two terminal network. Let me draw that. Let me draw that. You will understand. Yeah. Now, I'll just put a red box here. So that is your linear circuit. So this is linear. Everybody understand that? So whatever is within the box is your linear two terminal network. See, this is your linear two terminal network. This linear two terminal network now needs to be converted into a Thevenin's network. What is this? This is Thevenin's network. Here, this is Thevenin's network. What is Thevenin's network? Thevenin's network is a voltage source in series with the resistance. Understand that? How this can be obtained? Given any linear two terminal network, we can obtain VOC and RT. How to obtain that is what we're looking at. So what is the question? Question goes like this. Everybody look at this. Question goes like this. Find the Thevenin's equivalent network across the terminals A, B. This is what is the question. So across the terminals A, B, you have to find out the Thevenin's equivalent circuit, means you have to find out RT and VOC. Okay. So in the solution, we shall say this. In the solution, we should say this. What is that? Thevenin's network is, yeah, Thevenin's network is this, plus minus Thevenin's voltage, which is open circuit voltage, and Thevenin's resistance. Everybody understand? So what is that first we are doing? First, let's find VOC. To find VT, which is your VOC. Everybody understand this? So we need to consider this circuit now. Okay, the circuit that we have here needs to be considered for finding out VOC. Okay, so let me copy that here. Fine. Now let me just take this. Everybody just copy that down, copy that circuit down, everybody. Yeah. Yeah. Now everybody copied down that circuit. Now what we shall do is marking this voltage. So this is the given circuit. So what we need to do here is we are finding out VOC, right? What is VOC? VOC is the open circuit voltage. So first thing what we have to say, mark VOC as shown, because that is what we are trying to find out. This and this VOC itself is your Thevenin's voltage. So now here you can find out VOC by mesh analysis or node analysis. In module number 1, what was happening when we were learning the basic concepts? They were very particular in saying, see, you have to find out a voltage by mesh analysis only, or you have to find out the voltage or current by node analysis only, or by source transformation and shift only. But here in this chapter, nobody will be insisting you to find out any voltage or any current by any particular method. It is left to you to find out to decide a suitable method or feasible method to find out the voltage here. So which method do you think is good here? So there is just one mesh. There is no current flowing here. So it is one mesh. So let me solve this problem by mesh. I'll not say I'll solve this problem by mesh analysis. I'll just mark the current. Okay. So we have marked VOC. Then I'll say I'm marking I1. Okay. So mark I1 as shown. So why we are doing that? To find out this VOC. Understand that? So soon after I mark I1, it is understood that I am solving this problem by mesh analysis. So in mesh analysis, what do? I apply KVL. So KVL to mesh 1. There's just one mesh and let's call that as mesh 1. So let's start from here. It's minus 50 plus 5I1 plus 20 I1 equal to 0. So it's 25 I1 equal to 50, which implies that our I1 is 2 amps. Is this okay with you, everybody? So if I1 is 2 amps, how to find out VOC is the question. So for finding out voltage across open circuit terminals, what I used to tell, do you remember? Anybody, if you remember, can tell me what to do if you have to find out voltage across open circuit terminals? Anybody remember that? Anybody remember that? So we form a dotted path. See, I'm forming a dotted path. I'm very particular in calling this as dotted path only. Why this is a dotted path? Because in this path is not a complete path. It's not a closed path. So it is a dotted path. So what I'll do, I'll apply KVL to the dotted path. Understand that? KVL to the dotted path to find out VOC. KVL to dotted path. Actually, we should not be applying KVL to any path which is not closed. But here we can do it. Everybody just observe. I'm not showing any current here, mind you. I'm not showing any current because the current will not flow in this particular path. Why the current will not flow in this particular path? Because it's not closed, it's open. Understand? But I know VOC is here. Is there any current flowing through 4 ohms? Anybody? Is there any current flowing through 4 ohms? No. See this I1 after coming at this point, all I1 would flow through 20 ohms because through 4 ohms nothing enters because this is open circuit, infinite resistance, mind you. So no current enters this branch, this open circuit branch. Okay, so whole of the current would come through 20 ohms and keeps rotating in this particular path only. No current enters this. So if I apply KVL in this direction, so I'm moving upwards. Current I1 is moving downwards, so it is minus 20 I1. Everybody is okay with that? It's minus 20 I1. Now comes 4 ohms. Now comes 4 ohms. Let's say plus 4. What is the current that is flowing through 4 ohms? 0, mind you. There is no current flowing through 4 ohms, mind you. Then comes this VOC. Okay, so it's plus VOC equal to 0. So what does this imply? Our VOC is 20 into I1, that is 20 into 2. So VOC is 40 volts. We can say, therefore, our VT, which is the open circuit voltage, is 40 volts. So what we have done now, we have found one of the parameters required to find out the Thevenin. This we have found out now. We have to find out this RT. So what we have to do to find out RT is the question. What did the procedure say? To find out RT, we have to deactivate all the independent sources. What is deactivating independent sources? Let's see. Okay, everybody just concentrate. Okay, what we are doing is to find RT. So what is the first step that we need to do here? What is the first step? Everybody, deactivate the independent sources. If there are dependent sources, we're not supposed to deactivate them. We have to deactivate only independent sources. Okay, independent source means that is short circuit what? Voltage source. Okay, and open circuit what? Current source. Everybody understand? In this particular given network, we have been given a voltage source, right? So voltage source needs to be what? Needs to be deactivated. Deactivating 50 volt source means short circuiting 50 volt source. So what do we do here? What do we do here? Short circuit 50 volt source. This is what deactivating the sources means. Okay, short circuit 50 volt source. So what do we have now by short circuiting? What we will be having, see here, everybody, by short circuiting, what is we are going to have? See here, the voltage source is short circuited. So if you want, you can say we have short circuited this. Okay, then we have a 5 ohm, we have 20 ohms, we have 4 ohms. Everybody understand this? So this is 5 ohms, this is 20 ohms, and this is 4 ohms. Okay, and where will be your RT? Your RT is this. So we have short circuited. See here, there was a 50 volt source, so that we have short circuited. Let's take this now. Let's find out RT. What is RT now? Everybody calculate RT. Calculate RT now, everybody. What is RT? We can just write here. Therefore, RT is 5 ohms. Sorry, 5 ohms in parallel with 20, and this parallel combination is in series with 4 ohms. What is 5 parallel 20? It's 5 into 20, okay, divided by 5 plus 20. Okay, this plus 4 is there anyways. So what is this equal to, everybody? What is RT? Okay, so it is going to be 5 into, this is 100 by 25, it's 4 plus 4. Your RT would be what? 8 ohms. Everybody understand this point? So what was needed that we have found out? We had to find out VOC, so that we have found out. We had to find out RT, that we have found out. Okay. So therefore, what is the network? Therefore, the Thevenin's equivalent network across terminals AB is what? Is this? You have to write the values. Okay. So this we have obtained as 8 ohms. Okay. And this we have obtained as 40 volts. Is this okay with you, everybody? Is this fine? I'll just repeat what we have done. Okay. We were asked to find out the Thevenin's equivalent network across the terminals AB. When the Thevenin's equivalent network is asked, you should see for a linear two-terminal network where the two terminals are open like this. Okay. So Thevenin's equivalent network means you have to be finding out the open circuit voltage, which is Thevenin's voltage, and the Thevenin's resistance. What is Thevenin's voltage? Thevenin's voltage is the open circuit voltage that we mark across the open circuit terminals AB. Use any method that you want to find out VOC, whether you use mesh analysis or node analysis or source transformation, it is left to you. But you should be smart enough to see that which method takes the least time. Okay, that method you should go for. Fine. So time saving is very important here. So that is, so by mesh analysis we have found out our Thevenin's voltage, it is open circuit voltage. Then to find out RT, what did we do? We deactivated the independent sources. What is deactivating the independent sources? If you have a voltage source, short circuit that. If you have a current source, open circuit that. Since there is a voltage source, okay, we have short circuited that voltage source. That's why I've written SC here. You can write this or you can just leave that, not a problem. Then find out the equivalent resistance after deactivating the independent sources. Okay, and that is your Thevenin's resistance. And that after finding out your VOC and VRT, we have your Thevenin's equivalent network. I hope everybody understands this part. Is this okay with you? Let's go with another problem. Everybody, copy down this. Let's go with another problem. That is this. Problem number 2, everybody. Copy this. Everybody. Fine. So this is 20 volts. This is 6 ohms minus plus 2I, 10 ohms and 6 ohms. Where is this I flowing? This I is flowing here. This I. And these are A, B. So what is the question again? Question is same. Find the Thevenin's equivalent network across terminals AB. Now this is little different. What way it is different from the first problem that we saw? So in the first problem we have only the independent source. Okay. In the second problem we are having the dependent source. We have independent source also. We have dependent source also. Understand that? So it is plus minus. Now what is that you should understand is the method of finding out VOC would not change. Understand that? Method of finding VOC would not change because it is VOC that we draw across this. But when we are finding out RT, what we did do here, we deactivated the independent sources to find out RT. But after you deactivate the independent sources, the dependent source is still there, which is not supposed to be deactivated. So the method of finding out RT differs here. Okay, the method of finding out RT would differ because we cannot find out RT by deactivating both of this. No. And when there is a when there is a dependent source which we cannot deactivate, you cannot find out the equivalent resistance across AB. So that needs to be learned here. Everybody understand? So I hope you have copied that. Let's go on with the solution. Since they have asked us to find out the equivalent Thevenin's equivalent network, the first thing that we have to find out is what? What? VOC, right? So let's say to find VOC is equal to VT. Let's not write the circuit first itself. You should remember that I need these two. I need these two. RT needs to be found out. Okay. VOC needs to be found out. So for first, what we are doing? We are doing finding out VOC. So what is this? Okay. And what is this? Across terminals AB. So let me directly do it here. So again and again, copying the circuit will take time. So while finding out VOC, we can mark VOC in the circuit that we write in the question itself. Okay, this is your VOC, and you know VOC is your VT. Every time I'll not write that. Okay, but I'll say in the problem that mark VOC as shown. Mark VOC as shown. So we have marked. Again, as we did in the previous problem, let's do the same to find out VOC. What is that? Marking current I1. See, I'm marking I1. I is flowing here, mind you. You have to be a little careful. Okay. Now, what is I equal to? What is I equal to? I is equal to I1 because this I would not flow in through this 10 ohms. Why it would not flow through this 10 ohms? Because 10 ohms is open circuit branch. So the current will not flow. So this I which is flowing through 6 ohms will flow across all these, and that is where your I1 is also flowing. So let's find out let's write the equation, okay, and then do that properly, okay, and bring that into proper form. So KVL to mesh 1, okay, everybody. KVL to mesh 1. Okay, so it's minus 20 plus it's minus 20, okay, then 6I1 minus 2I plus 6I1. This is what I'll write, okay, and the equation that we write here, the KVL that we write here, should be only in terms of the mesh current. Okay, so there is a branch current I. What is this branch current I equal to? Is it not your I1? Yes, it is I1. So substituting I equal to I1. Why we need to do this? Because in mesh analysis, I need KVL only in terms of the mesh currents. In node analysis, I need KCL only in terms of the node voltages. Let's remember that. Okay. So what would this be? So it would be minus 20 plus 6I1 minus 2I1 plus 6I1 equal to 0. 6 and 6 would give you 12. 12 minus 2 is 10 I1. So it is 10 I1 equal to 20, which means that our I1 is 2 amps. Everybody understand that? I1 is 2 amps. But we need to find out what? We need to find out VOC. To find out VOC, what do we do? What do we do? As we have done in the previous case, we draw the dotted path. Okay, so let's draw the dotted path here also. Fine. Here, I'll draw the dotted path here. I don't want to call it as mesh 2. I've told you the reason, because it's not a closed path. And no current is flowing. Only the current is flowing through 6 ohms. There is no current flowing through 10 ohms. Okay. So what we have done to find out VOC? Apply KVL along the dotted path. Everybody do that. Apply the KVL along the dotted path and see what we get. Do this. We are left with 3 minutes. I hope we will be getting it within it. Yeah, I'll draw that. I'll just do that here. It's minus 6 I1 plus 10 into 0 plus VOC equal to 0. So this is your what? The KVL along the dotted path. I'll just take this. Okay. So this is VOC. Therefore, VOC is what? 6 I1, and that is 6 into 2. So therefore, we can say our VT, which is VOC, is 12 volts. Is this okay with you, everybody? We have to find out RT. So how to find out RT when the dependent source is there is something that we'll take up in the next session.